When a plane wave in one media encounters a different media during its travel, two things can happen: a reflection to the first media and a transmission to the second one. In this section, we consider the scenario of a uniform plane wave, which is normally incident on the interface between two dielectric media. By normal incidence, we mean that the direction of propagation is perpendicular to the boundary. So as shown schematically, we have two media, medium 1 on the left and medium 2 on the right. The blue one that is shown in the figure is the interface between the two media. As an example, medium 1 can be air and medium 2 can be glass. So we are on the process of finding out how the propagation of electromagnetic wave traveling along the z direction be affected when it is traveling from medium 1 to medium 2. During its traverse from medium 1 to medium 2, the electromagnetic wave can be reflected or transmitted according to the material parameters of the two media, that is epsilon and mu. We are studying the case of normal incidence, that is the propagation of the electromagnetic wave is along the plus z direction, normal to the interface. Let us assume that the velocity is v1 in medium 1. The electric vector in the incident wave is polarized along the x direction and it is represented by vector EI. The magnetic field is polarized along the y direction and it is denoted by BI. So EI and BI denote the incident electric and magnetic fields. As it propagates along the positive z direction, depending on the permittivity and permeability of the medium that it is encountering, it can be completely reflected or completely transmitted, or it can be partially reflected and partially transmitted. Let us assume that the reflected wave travels along the negative z direction with a velocity v1. So the reflected wave propagates in the same medium, that is medium 1. The reflected electric vector remains along the x direction and is denoted by ER. However, upon reflection, the direction of the magnetic field will be reversed and it will be along the negative y hat direction. The magnetic field reflected is indicated by vector BR. If there is some kind of a transmission inside medium 2, then the wave will be traveling along the plus z direction with velocity v2. The electric vector of the transmitted wave is denoted by ET and it is polarized along the x hat direction. For the kind of transmission that we are considering, there is no phase change for the magnetic field and it is still along the y hat direction. The magnetic vector is denoted by vector BT. So as per the setting, the xy plane forms the boundary between the two linear media. We assume that a plane wave having frequency omega approaches the interface from the negative z direction towards the positive z direction. The wave is polarized in the x direction. So we write the incident electric and magnetic fields as EI and BI. This is a vector as well as a complex quantity dependent on z and t. This is equal to E0I, which is again a complex entity, e raised to I k1z, where k1 is the propagation vector, minus omega t polarized along the x hat direction. And the magnetic field is B0I e raised to I k1z minus omega t polarized along the y hat direction. In terms of the electric field, this equation can be written as E0I divided by V1 e raised to I K1 Z minus omega t y hat. Now let us write the equation for the wave that is reflected back towards the negative z direction. Since the reflection is in medium 1 itself, we can write ER and BR as the reflected electric and magnetic fields, and then ER is equal to E0R, then e raised to I negative of K1 Z minus omega t x hat, and then BR is negative of E0R divided by V1, then e raised to I K1 Z minus omega t y hat. The negative sign for K1 Z is because the wave is traveling in the negative z direction. Now, why is there a negative sign for the magnetic field? This can be understood by considering the Poynting vector, which is 1 by mu 0 times E cross B. Now, after reflection, the wave is propagating along the negative z direction. Since the wave is propagating along the negative z direction, the energy flow, that is the Poynting vector, also has to be along the negative z direction. And this is possible only when the direction of B is reversed. That is, the Poynting vector S is 1 over mu 0, then E along x hat cross B along negative y hat. This is equal to EB over mu 0, then x hat cross negative of y hat, and this is equal to EB over mu 0, then negative of z hat. That is, if the Poynting vector has to be along the negative z direction, the direction of polarization of B has to be reversed. That is, upon reflection, the magnetic field has to be along the negative direction, that is the negative y direction. Now, the wave that is transmitted to medium 2 can be written as ET ZT. This is equal to E0T e raised to I, since it is in medium 2, K2Z minus omega t polarized along x hat direction, and then BT is equal to B0T e raised to I K2 Z minus omega t polarized along y hat direction. We are already familiar with the boundary conditions that are to be satisfied by E and B when the electromagnetic wave travels from one media to another. Condition for the perpendicular component of the electric fields on either side of the interface is epsilon 1 E1 perpendicular equal to epsilon 2 E2 perpendicular. For the magnetic field, it is B1 perpendicular equal to B2 perpendicular. As we are considering a dielectric media which is devoid of any free charges or free currents, the equation for the parallel components are E1 parallel equal to E2 parallel. The equation for the parallel component of the magnetic field is 1 over mu 1 B1 parallel equal to 1 over mu 2 B2 parallel. The fields in medium 1 are EI and then ER, BI and then BR. And those in medium 2 are ET and then BT. According to the boundary conditions that we have written, at the interface, the combined fields on the left, that is EI plus ER and then BI plus BR, has to join the fields on the right, that is with ET and BT. From the figure, it is evident that there are no components of E and B which is perpendicular to the interface. Therefore, equation 1 and equation 2 are trivial. However, that is not the case with equation 3, which gives the boundary condition for the parallel component of the electric field. Since there is a finite parallel component for the electric field, from the third equation, E1 parallel equal to E2 parallel, we have E0I plus E0R equal to E0T. This is also true for the magnetic field, which has a parallel component at the interface. Therefore, from equation 4, which is 1 over mu1 B1 parallel equal to 1 over mu2 B2 parallel, we have 1 over mu1 B0I plus B0R equal to 1 over mu2 B0T. This is again 1 over mu1 times 1 over V1 E0I minus 1 over V1 E0R. This is equal to 1 over mu2 times 1 over V2 then E0T. When we simplify this equation, this is E0I minus E0R. This is equal to mu1 V1 divided by mu2 V2 multiplied by E0T. When we rewrite this equation in terms of the refractive index, we have mu1 then C over N1, where N1 is the refractive index of medium 1, and then mu2 times C over N2, then E0T. Let's take these two terms as a constant beta. Therefore, this equation becomes beta times E0T, where beta is equal to mu1 V1 over mu2 V2, and this is again equal to mu1 N2 divided by mu2 N1. We shall now solve equation 5 and 6 for the outgoing amplitudes to get expressions in terms of the incident amplitude. Let's have 5 plus 6. So this gives us 2 times E0I equal to 1 plus beta times E0T. And the transmitted electric field, this is equal to 2 over 1 plus beta then E0I. This equation tells us that not the entire electric field has been transmitted to medium 2, but only a factor which is determined by 2 over 1 plus beta. Remember that beta is dependent on the material parameters mu1 V1 N1 and mu2 V2 N2. So the percentage of the field that is transmitted will depend upon the factor beta. Now let us have equation 5 minus equation 6. This gives us 2 times E0R equal to 1 minus beta times E0T. When we simplify, we have 2 times E0R as equal to 1 minus beta. Then in place of E0T, we'll write 2 over 1 plus beta times E0I. The 2 and 2 gets cancelled and we get the expression for the reflected electric field as equal to 1 minus beta divided by 1 plus beta times E0I. We see that the fraction of the field that is reflected is again dependent on beta. Let's make further simplifications for equations 7 and 8. For most media, the permeability will be approximately equal to the permeability of free space. This is because most of the material media are sensitive to electric fields than the magnetic fields. Therefore, beta can be written as mu1 V1 divided by mu2 V2 approximately equal to mu0 times V1 divided by mu0 times V2. The two mu0s get cancelled, resulting in V1 over V2. Therefore, E0R is equal to 1 minus V1 over V2 divided by 1 plus V1 over V2 times E0I, and this is equal to V2 minus V1 over V2 plus V1 multiplied by E0I. And similarly, E0T is equal to 2 over 1 plus V1 over V2, and this is equal to 2 times V2 over V2 plus V1. And this has to be multiplied with E0I. You might note that these results are strikingly similar to the ones that we have derived for the waves on a string. And as in the case of wave motion at discontinuity, the reflected wave is in phase or right side up if V2 is greater than V1, and out of phase, that is upside down, if V2 is less than V1. Now the real amplitudes are related by E0R equal to V2 minus V1 divided by V2 plus V1 mod, then E0I. And E0T is equal to 2 times V2 over V2 plus V1 multiplied by E0I. In terms of the indices of refraction, E0R is equal to modulus of N1 minus N2 over N1 plus N2 multiplied by E0I, because we have V as equal to C over N and E0T as equal to 2 times N1 divided by N1 plus N2 multiplied by E0I. Let's now find out what fraction of the incident energy is reflected and what fraction is transmitted. For that, let us consider the intensity of the electromagnetic wave, which is the average power per unit area, defined to be I, equal to half epsilon V E0 square. We call the ratio of the reflected intensity to the incident intensity as the reflection coefficient R, which is defined to be IR over II. And this is equal to half epsilon 1 V1 E0R square divided by half epsilon 1 V1 E0I the whole square. Upon simplification, this becomes E0R square divided by E0I square. And when we substitute for E0R in terms of E0I, we have N1 minus N2 over N1 plus N2 the whole square, then E0I square upon E0I square. And the final expression for the reflection coefficient is N1 minus N2 divided by N1 plus N2 the whole square. So this is a fraction of incident energy that is reflected. Now let us try to find out the transmitted intensity or the transmission coefficient. The transmission coefficient is defined to be T equal to IT upon II. And this is equal to epsilon 2 V2 over epsilon 2 V1 multiplied by E0T square divided by E0I square. Let's do a simplification for epsilon 2 V2 upon epsilon 2 V1. That is epsilon 2 V2 over epsilon 1 V1. This can be written as mu 0 over mu 0, then epsilon 2 V2 over epsilon 2 V1. As we have previously seen, most of the material media are more sensitive to electric fields than the magnetic fields. So let us take mu1 as approximately equal to mu 0 and also mu2 as approximately equal to mu 0. And mu1 and mu2 may not be equal. Therefore, this equation becomes mu2 epsilon 2 in the numerator and mu1 epsilon 1 in the denominator multiplied by V2 over V1, and this is equal to V1 square divided by V2 square multiplied by V2 divided by V1, because we have V as equal to 1 over square root of mu epsilon. Upon simplification, this becomes V1 divided by V2, and because the refractive index N is C by V, this equation can again be written as N2 over N1. That is, the transmission coefficient is T. In place of epsilon 2 V2 over epsilon 1 V1, we shall write N2 over N1. For the transmitted intensity E0T square, we shall write 2N1 over N1 plus N2 the whole square, then E0I square. The denominator is E0I square. The two E0I's get cancelled, and with further simplification, it becomes 4N1 N2 over n1 plus n2 the whole square. So we see that the fraction of energy that is transmitted to medium 2 is dependent on the refractive indices of the two media. And always the sum of reflection coefficient and transmission coefficient will be equal to 1 as required by the conservation of energy. For instance, when light passes from air, that is a medium having refractive index n1 equal to 1, to glass, which is a medium having refractive index 1.5, the reflection coefficient is found to be 0.04 and transmission coefficient is found to be 0.96. So when we add R and T, that will be equal to 1. Because the transmission coefficient is 96%, we see that most of the light in air is being transmitted to glass.